Well, the plan for this video is to look at how we can calculate the volume of a solid in a special case, special volume I'm going to call this, where you could use a cross-section area function. Now, the idea here, if you got a solid that can be modeled in terms of a base, in this case we got a base bounded by y equals x squared and y equals 4. So here's a picture of the base right here of my solid. And then if the cross sections of the solid can be modeled, and in this case they can in terms of something whose area we know, in this case, the cross sections of our solid are squares. So, like right here, would be like one side of the square cross section of your base, and the height of the dimension of the square would be the same as this length right here. Like here's a picture of the solid with a hollowed out one side, and looking in, give a picture of a cross section. A square might not quite look like a square based on the perspective and the sort of scaling in the x, y, and z direction, but it is. So the notion here is that you could actually calculate the area of a cross section any place between y equals 0 and up here, say y equal to 4. By just looking at one of these cross sections, computing the length of the cross section, and squaring that, and you've got the area of the square cross section. You could approximate the volume of the solid if you actually put a little thickness to these square cross sections, and maybe filled the thing up with a million of them and calculated the volume of each of those 1 million thin little cross sections and added them up, get a pretty close approximation of the volume of the solid. But it turns out one of the beauties of calculus is you can do that a whole lot easier than trying to add up the volume of a million cross sections. So even trying to take the limit as that number of cross sections approach to infinity. Well, that's what you actually do in calculus, but the way you compute it is it's just beautiful. So this is what we're looking at here. Just to sort of picture a little bit more maybe before we compute it here. Here's a picture again of here's the base, and then here's a cross section, and you could actually notice that the cross section here getting larger as y is going from 0 down here to 4 up here, and so there are the cross sections, and I could actually show you the different point of view of the solid. Here's the solid all filled in but transparent, and you can see the cross sections there being sort of animated back and forth across it here. So the idea in calculus is you can come up with a cross-sectional area function. In this case, it's going to be as a function of y. It gives you the area of the cross section. You can use a technique called integrating in calculus to actually integrate that cross-sectional area function over the interval of values for y, which in this case would be 0 to 4, and come up with the exact volume of the solid. It's just remarkable what you can do with calculus. Here's the picture of the thing again. Turn it to the side there, and we can look at these cross sections I was talking about here. Again, you can see them now. I hope you can see them there from that side view. So anyway, that said, if we go back to my little PowerPoint here, and here are these two pictures I was looking at. Here's the base, here's the solid, and there's the cross section of it. Here's another view like I just showed. So you can calculate the volume of this thing remarkably by coming up with this cross-sectional area function, which, as I said, would be the x value here minus the x value there would be literally 2 times the x value here. And then you square that, get 4x squared, or since x squared is y, 4y is the actual area of a cross-section of this solid in terms of y. And so the base of it here, y goes from, we got model y goes from 0 up to 4, so I can actually integrate, it's my little calculus integration symbol, integrate from 0 to 4, the cross-sectional area function of 4y with respect to y. Find your antiderivative of 4y. Principle 1 is 2y squared, that's good enough to use. From 0 to 4, Fundamental Theorem of Calculus tells you put in 4 for y here. Get 2 times 4 squared minus, put in 0 for y, you get 0. 4 squared is 16, times 2 is 32. 32 cubic units. That's the exact volume of that solid that we were looking at. Isn't that cool? Calculus can actually compute the exact volume of that kind of solid. Pretty cool.